Hello again, everyone. Today's video is about operations on rational expressions. So this is just the start of our brand new unit on rational expressions and rational functions. Very, very exciting. I'm very sad that I'm not getting to do this right in front of you because this happens to be one of my favorite units of all time when it comes to Algebra 2. But it's all right. We're going to make it as exciting as we can digitally. So first and foremost, what is a rational expression? Well, it's an algebraic function for which both the numerator and the denominator are polynomials. Hence, we're doing this right after our polynomials unit. So some examples you see here, if we have x squared plus 5, that's a quadratic binomial, so that's a polynomial. And then we have a linear binomial on the denominator. So that would be an example of a rational expression. Our second example over here, x squared times y over x times z, that's also considered to be a rational expression. So we're going to look first at operations of these type of expressions. So that's going to be goal number one, and we're going to be able to simplify. Look at this. It's so exciting. We get to simplify stuff like this. Coming up, that's going to be goal number one, computing operations with rational expressions. After that, we're going to learn how to solve a rational equation. And last part of the unit, we are going to sketch graphs of rational functions. So we'll get graphs that look something like this, even though they do vary. And we'll learn some new vocabulary like vertical asymptote and horizontal asymptote. All right, so let's not get too ahead of ourselves. We have 3 goals before the end of the unit and before the end of the school year. Woo, I know we're all excited for summer vacation. So let's get started. Goal number 1, operations on rational expressions. We're going to start off with just adding and subtracting in this video. So adding and subtracting, if I have 2 over 5x plus 8 over 5x. So something to remember, all the operations that we're going through, they're just like back in elementary school. So back in elementary school, when you had to add and subtract fractions, you needed a common denominator. So the same thing goes here. We need a common denominator for adding and subtracting. And for our first example, 5x is a common denominator between both of these rational expressions. So we can go ahead and add them together. So we're just going to add our numerators together, which gives us 10. Our denominators, once they are in common, they stay in common. You do not add them. From here, we could try to simplify. Remember, you can simplify. Between multiplication. You cannot simplify between addition and subtraction. So you can simplify factors, not terms. That's something you're going to hear me repeat over and over and over throughout this unit. We can simplify factors, not terms. So what I mean here, if we're going to think about this as 10, can be rewritten as 5 times 2. Our denominator can be rewritten as 5 times x. So in that case, I'm going to cancel out the factor of 5 in both the numerator and the denominator, which is going to leave me with 2 over x. All right, so that is just one example of how we can add fractions together or add rational expressions. We do have to state here that there are restrictions. As we see from the graph, we get these things that are called asymptotes because there are certain values that x can never equal. Since we're dealing with fractions, we know that our denominator can never equal 0. So for us here, we just need to specify with our answer that x cannot equal 0. That has to be part of our solution, so that's considered a restriction, it is called. Let's look down at the second example. If we see here, we don't have that common denominator naturally. They look really, really similar though. So we have to think, well, how do I get the one fraction to have the same denominator as the second fraction? So it looks like all the second fraction is missing is that it needs to just be squared, which means that we need to multiply it by itself. In order to not change the value of the expression though, whatever I do to the denominator, I also have to do to the numerator. So that means, I'm just going to erase this. So that means I am going to multiply numerator and denominator by an x plus 1. Remember, to square something means to multiply it by itself. So because this is squared here, that means you have x plus 1 being multiplied by x plus 1. So I'm going to bring down my first fraction as is. Didn't touch it. Didn't need to. Second fraction, I'm going to distribute. So I get 3x 3x squared plus 3x over, and I'm just going to leave my denominator at x plus 1 quantity squared. There's really no need to have to factor that out right now, or FOIL that, excuse me, so I'm just going to leave it. If I combine my like terms, keep that in mind. Some people mess this part up on their polynomials test. We need to subtract this binomial from the original constant here. So just be careful with your terms. So I'm going to get negative 3x squared minus 3x plus 5. Ooh, I think I got it. Plus 5 over x plus 1 quantity squared. All right, this is not factorable. It's not something that can simplify. So I am just going to leave it as is. If the numerator was factorable and one of those factors happened to cancel out with a factor of the denominator, we would have to reduce it. Otherwise, we are done. All right, just answering the restriction part. So it looks like our restriction here, if we try to set any of these denominators equal to 0 and solve for x, x could not be negative 1. All right, so final answer. And let's move down to the next one. Just going to clean that up. Moving down to the next one. So it looks like on here, there is no common factor at all now between both denominators, right? Some people might be looking at it like, well, you have an x on the left, and you got an x on the right. So, right, all the right fractions missing is that minus 2. But we can't just stick a minus 2 at the end of it. I mean, that'd be kind of cool, and that would make it a lot easier, but it doesn't work that way. Sorry. So if we're going to take that suggestion out, that means that we have to multiply by each other's denominator. Since they don't have anything in common, that's going to be our method. So I'm going to multiply this first fraction by x over x. I'm going to multiply the second fraction by x minus 2 over x minus 2. All right, so let's distribute. For our first fraction, we get 4x squared. For our second fraction, we get 9x minus 18. And these are over x times x minus 2. All right, so let's, from here now, I'm just going to combine my like terms in the numerator, keeping in mind I am subtracting everything in that second fraction, so watch your signs, please. 4x squared minus 9x plus 18 is my numerator, and x times x minus 2 is my denominator. Let's look at restrictions. What can x not equal? Well, because of this one right here, because of that guy right there, we know that x could not equal 0. 0 times anything is 0. And then if we look to this guy here, well, then x can't be 2. Both of those values would make our denominator equal 0, which is a big no-no. So we have our final answer. Next set of problems, I'm going to ask for you to go ahead and try them yourself. So I'll just scroll up. I'll give you a moment to try those, and then you can go ahead and hit continue when you are ready. All right, it looks like our first example here, again, has no common denominator at all. So we're going to have to multiply by the other denominator, which means I'm going to multiply the second one by 4 over 4, multiply the first by 5x over 5x. All right, so when I multiply 5x by 5x, I get 25x squared over 20x. My second fraction, if I multiply by 4, numerator and denominator, I get 8 over 20x. When I combine those, I get 25x squared plus 8 over 20x. I'm not seeing anything in common to simplify there, right? If there is no GCF in the numerator to pull out as a factor, so there is nothing that I can do. Only thing I'm going to do is write the restriction here that x cannot equal 0. And my first problem's done. Second problem, again, there is nothing in common between that numerator and denominator. Between the denominator of the first fraction and the second fraction. So it means I have to multiply by the other one. So I'm going to multiply by 4s plus 1 top and bottom. I know, I'm sorry, S's and 5's in the same problem. Terrible, terrible. So in the second fraction, 5s minus 2 over 5s minus 2. All right, so first fraction, 4s times s, 4s squared. S times 1 is just s. Denominator is just going to be 4s plus 1 times 5s minus 2. We're subtracting again here. And then my second fraction, nice and easy, 5s minus 2 over 4s plus 1 times 5s minus 2. All right, let's try to see if we can combine some like terms here. That 4s squared is by itself. Let's see, I have an s minus 5s is going to be minus 4s. And then I have a minus negative 2. Did that trip you up? Some people might have fallen for that one. This is going to end up being a positive 2 at the end. From here, our denominator is going to stay the same, 4s plus 1 and 5s minus 2. Oops, I put an x by accident. And then it looks like the numerator is factorable. So I am just going to look there next to see if there's something that can be simplified. It's possible that it's not, but at least I know I can pull out a 2 as a GCF, which would give me 2s squared minus 2s plus 1. Is that further factorable? I think not. So it doesn't make a difference here. You can leave your answer in this first form here, or with the 2 pulled out as the GCF. Either of those answers is 100% acceptable. One is not more correct than the other one. I just wanted to try and see if there's something I could simplify, because all of your directions throughout the entire unit is always going to say simplify as much as possible. Restrictions, last part of the problem before we move on. What can our denominators not be? It looks like s cannot equal, I got a negative 1/4 and a positive 2/5 as a denominator. All right, so I'm going to actually circle all of this because that's all part of my final answer. All right, last problem. Last one. This one had a common factor, if I remember correctly. So let's take a look. If I factor my first fraction, the denominator anyways, I get j minus 1 and j plus 1. It's a difference of squares. Okay. Second fraction, I get j minus 1 over, this is j minus 6 and j minus 1. So they both at least carry that j minus 1 factor, the difference being that other factor. So I'm going to multiply by just that other factor. So that means I have to multiply my first fraction by j minus 6, top and bottom. And then I'm going to multiply my second fraction by the j plus 1 that it's missing. And then j plus 1. All right, so for my numerator, then on the first fraction, I get 2j squared minus 12j. I'm adding here, so I'm just going to go ahead and bring on to that. I have to FOIL. Be careful here, make sure that you FOIL and you get j squared minus 1. My denominator is all 3 of these factors here. And j minus 6. All right. Let's see. I know we can combine a little bit. I got a 3j squared minus 2j minus 1. That is definitely not factorable. Leaving all of my factors in the denominator. Resist all urges to distribute, besides the fact that it's totally not necessary. When it gets to graphing, you actually really don't want to have this distributed. So it's just best to get into the habit now. All right, so we got our final answer. Last piece of the puzzle, we need to put in our restrictions so we know that j cannot equal. Looks like we have a 1, a negative 1, and a 6. All right, so that's all of our examples today for adding and subtracting rational expressions. Please stay tuned for our next video where we'll go over multiplying and dividing rational expressions. Thank you so much for watching.